9-2. We're solving two variable linear systems. So yesterday we talked about graphing and substitution. We did linear and nonlinear. As we're doing this method today, which is elimination, we're going to be doing only linear systems. We've done this before. Elimination means eliminate, right? If you eliminate one of the variables, you can find out what the other one is. Then you can do the whole back substitution thing and you're good to go. That's all there is to it. Easy stuff, just like everything else we do in this class. Okay. So elimination. I have two equations here, 3x plus 5y equals 7 and negative 3x minus 2y equals negative 1. This system is already set up for elimination. By looking at this, if I combined equation 1 and equation 2, 3x and negative 3x means I have no x's. 5y minus 2y gives me 3y. 7 minus 1 is 6. What's y?
2.
Y is 2. Divide both sides, right? Now, what do you do with that 2? Plug it into what?
X. Y.
Which equation? It does not matter. Does not matter. Anybody have a preference? Would you rather plug it into equation 1 or 2? Why 1? Okay. Yeah, we have x to solve for left, right? I would prefer that x term to be positive. So my choice would be plug that 2 into the first equation. That's a positive 3x. And that's the only reason. I would get the same answer plugging it into the second equation as well. So there you go, elimination. So this one was nice. The x's are already set up for us to eliminate. Working through that problem, we get y equals 2. Yay. Okay, so process. To use the method elimination to solve a system of two linear equations, perform the following steps. Number 1, obtain coefficients for x or y. It doesn't matter which one you eliminate, to make them have opposite signs. Okay, not just opposite signs, but opposite values, because if they have opposite values, once you combine them, they'll be gone. Step number 2, add the equations to eliminate that one variable. Step number 3, solve the equation that's left. Step number 4, back substitute into either one of the original equations to solve. And step number 5, check your answer. I don't know, it's a gnat. Okay. Whatever. Well, sometimes I can't teach when y'all are here. I didn't say it. Okay, two systems. If I combined them as it is, does anything go away? No. So we have to make a decision. We can get rid of x's or we can get rid of y's. Okay. There you go. Exactly right. In order to get rid of x's, we would actually have to multiply both equations by something. Okay. Whereas if we decided to get rid of y's, we only have to multiply one equation. Okay, you do it your way. We're going to do it the good way. Okay, you do it your way. We'll be done way before you. So which equation do you want to multiply? Second equation by 4. Okay, we're going to multiply equation 1, which happens to be the second one. I don't know why they did that. Okay, so we're going to take the second equation, multiply it by 4. So we're leaving equation number 1. We're leaving equation number 2 alone, which is 2x minus 4y equals negative 7. By multiplying equation 1 by 4, we get 20x plus 4y equals negative 4. And when we combine, we get so x is equal to I'm going to go with -1/2 if it's okay with you.
Because 22 divided by.
It's 11. It's 11 divided by 22, right? Okay. What would y'all like to do with 1/2?
Plugging it into the. Wait, no, I was looking at the bottom one. Because.
That's exactly right. Yeah. So I could plug it into either equation 1 or equation 2. Because equation 1 has an odd coefficient, half of an odd number is going to leave me with a decimal. I'll try to avoid that. So I'll take that -1/2 and plug it into equation 2. So I have 2 times -1/2 minus 4y equals -7. That gives me -1 minus 4y, -7, solving for y. Okay. Three halves. 6/4. 6/4 reduces to 3 halves, right? So the solution to the system is? And then, of course, we go through and check them. You would actually plug those numbers into both equations to check it. Okay. Questions on this? Okay. I'm going to erase all of that there. It's gone. Boom. Uncover what they did. See if they did the same thing. So far, so good. Exact same thing. Next slide. Exact same thing we did. Checking the solutions. They plug them both in. Plugged in for X, plugged in for Y. Do the math. They both check. And we conclude that the answer is good. So the last example, the two systems where 2x minus 4y equals -7, 5x plus y equals -1. And the equation 2x minus 4y equals -7, 20x plus 4y equals -4. Those are equivalent systems. They're equivalent because all we did was we took one equation and multiplied it by a scalar. If you take an equation and multiply it by everything by the same number, it's going to change the appearance of the equation, but the value of the equation is going to be exactly the same. The operations that can be performed on a system of linear equations to produce an equivalent system are: we can change the equations, exchange them. We can multiply an equation by anything but 0. Don't ever multiply an equation by 0, because then you have no equation, right? Kind of obvious there. And number 3, we took elimination a little bit to extreme. Yeah. Number 3, adding a multiple of one equation to any other equation in the system. That's what we've done. It is possible for a general system of equations to have exactly one solution. That would be, again, we're talking about lines. Exactly one solution means those two lines intersect. It's possible to have 2 or more solutions. Okay. If you're talking about lines only, it's impossible to get 2 solutions. You cannot have 2 lines touch twice. Because one line would have to be bent, and it's not a line anymore. 2 straight lines can only touch not at all, once, or infinitely many times. Okay. So if a system of linear equations has 2 different solutions, it must have infinite number of solutions. For a system of equations to have in 2 variables, the number of solutions is one of the following: exactly one solution, infinitely many solutions, no solution. No solution means the lines are parallel. Infinitely many solutions means the lines coincide, they're the same line. Exactly one solution, they cross once. Notice for infinitely many solution and no solutions, they have the exact same slope. Kind of makes sense, right? Parallel lines, same slope, same line, probably the same slope, common sense. Consistent. If there's at least one solution, the system is consistent. So a system can be consistent with one solution, or it can be consistent with infinitely many solutions. If it's inconsistent, that means no solution. Inconsistent. They don't cross each other. No solution. Dependent and independent. If there is one solution, what are the two lines doing? Intersecting once. They're going their own way, right? Isn't that what independent means? Independent means you're going on your own. Okay. Dependent means you rely on something. So if you have two lines that lie on top of each other, okay, that's a dependent system. Yay, yay, yay. 9-2 is pretty simple. Recognizing graphs of linear systems, match each system of linear equations with its graph. Describe the number of solutions and state whether the system is consistent or inconsistent. Okay. Look at the equations in letter A. Do you notice anything about the equations in letter A? They're the same because, Caddy, what were you going to say? They're multiples of each other, right? If I took this top equation and multiplied it by, oh, are they exactly the same?
Yeah.
Are they exactly the same?
Wait, no, they aren't. Sorry. Wait.
Are they exactly the same?
Yes. Well, they're the same line, but they're one of them
Okay.
is negative, one is positive.
Yeah,
Why would you not?
they're not the same. So if I took this system and multiplied it by 2, 4x minus 6y equals 6. This one's negative 4x plus 6y equals 6. Are they exactly the same? Okay. Are they exactly the same?
They're just like, are they not the same? They're the same except for the sign. So you can just cancel that one sign.
Okay, look at C.
Yeah, see, it's on, when you combine them, it's a no zero equals 12. It's a no solution.
Okay. So if I multiply the top equation by 2, I would have 4x minus 6y equals 6. Combine those and what do you get? 0 equals 12. How does that make you feel?
Oh, that's not supposed to happen.
Is that true?
No.
So that's inconsistent, right? 0 does not equal 12. It's inconsistent. So what does that tell you about these lines? Okay. So these two go together. We have no solutions because we are inconsistent. Okay. Jump over to C. What happens to C? They're exactly the same. So if I took that first equation in C and multiplied it by 2, what would I get? 4x
Minus 6y equals 6.
Combine those.
You get nothing. 0 equals 0.
Okay, that's a true statement. Both variables were eliminated, which means we only have one equation. Okay, so this guy is over here. We have how many solutions? Infinitely many.
I bet it's the A corresponds.
Which means it's consistent.
So is 2 dependent or independent? Because they like lay right on top of each
Okay,
other, but
this
not-
one is dependent because the lines lie on top of each other. Okay,
Okay.
what is this? You do not talk about dependency if it's inconsistent. If you tell me a system is inconsistent, you're done. No solutions, inconsistent, done. Okay? Infinitely many solutions, consistent, dependent. This one over here, one solution, consistent, and dependent. Obviously, it's going to be this one. So this guy goes over here. We have one solution. We have consistent. And we have independent. And this question didn't ask to label it as dependent or independent, did it? That's just bonus. Okay. Thoughts? How we doing? Brody, you all right? You're back there kind of cross-eyed, like you zoned out so far.
For some reason, confused me really bad.
Okay. A, the graph of system A is a pair of parallel lines. The lines have no point of intersection, so the system has no solution. It's inconsistent. B, it has a pair of intersecting lines. The lines have a point of intersection, so the system has exactly one solution. The system is consistent. And C, the graph was a pair of lines that coincide. The lines have infinitely many solutions in intersections. The system has infinitely many solutions and consistent. Applications, word problem. At this point, you may be asking the question, how can I tell which application problem can be solved using a system of linear equations? The answer comes from the following. Number one, does the problem involve more than one unknown quantity? We need to know that. Number two, are there two or more equations or conditions to be satisfied? If the answer to one or both of these is yes, then the appropriate model for the problem may be, right? Doesn't have to be, may be a system of linear equations. An airplane flying into a headwind travels the 2,000-mile flying distance between Massachusetts and Utah in 4 hours, 24 minutes. On the return flight, the airplane travels this distance in 4 hours. Find the airspeed of the plane and the speed of the wind, assuming that both remain constant. So the second the plane takes off, it's already at full speed. That's what it says, right? And then as soon as it gets there, oh, it stops. That's an abrupt stop. So someone's got whiplash. Okay, so thoughts on this? We're flying from Massachusetts to Utah. It takes 4 hours, 24 minutes. But flying back, what's that mean? Okay. Okay, so we crashed into the water now.
No, slow you down.
Okay, so talk about the speed of the plane. Positive or negative? I hope so. Okay, so we're going from Massachusetts to Utah. So we've got the speed of the plane. Four hours, 24 minutes. Okay, how fast is the plane going? Okay, how about this? Let P equal plane speed. How's that? Now let me ask you this. How fast is the plane going? P. There you go. Now, next question. How fast is the wind going? Don't know. So what do you want to call it? Okay. Let W equal wind speed. We're going from Massachusetts to Utah. How long is the flight? And the distance of the flight is?
2,000 miles.
Okay. Now, that 2,000 miles is composed of two components. It's composed of the distance flown by the wind speed and the distance flown by the airplane speed. Okay. We don't know how fast the plane is going. I don't know. What's 24 divided by 60? Is it a nice number? I think it is. I think 24 divided by 60 is a nice number.
Wait, what? 60?
24 divided by 60.
0.4.
Okay, so this right here is 4.4 hours. So going from Massachusetts to Utah, I'm going to travel 4.4 hours. And during that 4.4 hours, I'm being affected by a positive plane speed and a negative wind speed. Does that make sense? I'm flying against the wind. Okay. Let's distribute that and clean it out. That gives us 4.4 P minus 4.4 W equals 2,000. Now flying back.
Flying back, are you flying also headwind?
The wind's probably only going one direction.
So it's coming from behind you. So it's
Okay.
positive opposite.
There you go. So how long are we traveling from Utah back to Massachusetts?
So 4 hours.
4 hours. But now we have the plane speed, but we're flying with the wind,
So plus W.
but we're still traveling 2,000 miles, which gives us 4P plus 4W equals 2,000. So here's equation 1, and here is equation 2. We're doing elimination with ugly numbers. And we're done. Everything's eliminated. Don't worry about the problem. Okay. Using elimination, what would y'all like to get rid of? What would be the easiest to get rid of? The wind. The wind, because one's positive, one's negative. Okay. So, what do we,
You can multiply the
okay, that would give us 8.4 P minus 0.4 W equals 4,000. I did not eliminate a variable.
no, what you got?
What you got? Multiply 4 and this one by 4.4. That makes sense to me. I'm going to multiply this one by 4. So 4.4 times 4 is, I think, 17.6 equals 8,000. And if I multiply this one by 4.4, I get 17.6 P plus 17.6 W equals 8,800.
What is it? Yeah. 88.4880.
Are we good to go? Eliminating?
Yes.
Is it about that time already?
We've got 14 minutes.
We got 14 minutes. What are you doing? Okay. Combine 35.2 P. Y'all can check.
Just eliminate 17.6 already.
That's kind of what we're doing.
Oh, yeah.
35.2 P. Wind is gone. Is 16,800. Y'all check my math. I'm just doing this in my head. What's P? Divide both sides by 35.2. Point 2727. What's that? 2/11? I don't know. Subtract the 477 and do math enter on what's left. Do 16,800 divided by 35.2. Get an answer. Subtract 477 and do math enter. I have no idea what I'm talking about. Did it not work? Start over. Divided by. So subtracting 47, math enter didn't do anything when you subtracted the 477. Okay, so I'll just do math enter here then.
I got it like the fraction. Yeah, that's 34.
Okay. 477 times 11 is 52. Do what? 3/11. Okay. 477 and 3/11.
What's different about yours that you got a fraction and we did not? You have to put it in, so you have to get a.
I didn't subtract first. I just did math enter right there. Okay, now that I have a value for P, I can take that value and plug it into either one of the original equations to solve for W. And I'd probably work with the decimal to plug it in there and you'll be all right. I'm going to go ahead and move on and show them working it out. So they might approach it a different way, and that's fine. R1 is the speed of the plane, R2 is the speed of the wind, R1 minus R2 is the speed against the wind, R1 plus R2 is the speed with the wind. That's fine. No big deal. Using the formula, distance equals rate times time. That's what we had. That's what we had, right? 4 plus 24/60. Okay, all's well. Combine the equations. They got rid of R2, but I don't even remember what R2 represented. That's why I used P and W. Moving on. They got the speed of the plane to be about 477.27 and the speed of the wind to be about 22.73. And again, that'd just be a matter of plugging stuff in. And if I'm not mistaken, that's it. Folks, that's 9-2.